will be about our use of optical tweezers. There are two parts to this experimentation where we will be talking about Brownian motion and then observing the relationship of the holding force, velocity of the sample, and the intensity of the laser. Now, before we begin, I'd like to introduce the apparatus and its objective and applications. Basically, in optical tweezers, a collimated laser is focused onto microscopic particles, and they are able to trap the particle and manipulate its motion suspended in the given medium. This is because light itself, having momentum, exerts a force onto the bead, so that ultimately the bead experiences an attractive and repulsive force when optically trapped. This force being only in the units of a few pictonewtons. Now, in Thorlabs tweezer, we can see from the figure the beam is expanded, then this direction is changed by the mirrors, and so that it travels eventually to the objective microscope with the camera all the way down to the sample, but we're going to talk more about this. The father of optical tweezers, Dr. Arthur Askin, began his development of the apparatus from the 1860s, and by 1984, he had created the tweezers and demonstrated their function. And he noticed that particles more than 25 nanometers cannot be held anymore. And this work eventually led him to win the 2018 Nobel Prize. Optical tweezers have a variety of purposes in molecular biology, nanotechnology, pharmacy, and medicine. They're not able to just trap beads, but we can manipulate bacteria, DNA strands, and other small organelles. There are studies where they use tweezers to understand the interaction between proteins and DNA and how viruses function and other similar concepts. Now, to introduce how the system works, we need to understand the parameters. We assume that the bead is dielectrical, linear, isotropic, and spatially non-dispersive. The laser has a Gaussian intensity distribution, and so when this beam hits the bead, basically some of the light is either refracted into the bead or it is reflected, applying a momentum to the bead, and this in turn affects what forces are applied that keep it within the beam waist. We can define these forces into two components. The force that keeps the bead attracted to the beam waist is known as the gradient force, and the force that pushes it away from the beam is known as a scattering force. Another factor to consider is the Brownian motion that the bead will naturally have. Therefore, it is constantly leaving the center of the beam waist, and the gradient force has to bring it back to the equilibrium. This consistent cycle of springing in and out, as we can see from the diagram, it's similar to a harmonic oscillator and therefore can be described by Hooke's law. Now, how we define these forces is based on the size of the object in relation to the wavelength of the laser. And if the radius of the bead is much smaller than the wavelength, we can expect a Rayleigh scattering regime. And if the radius of the bead is greater than the wavelength, we can approach the forces with a geometric approach. Now, since the bead is very small, we can assume that the beam is hitting it. It is subjected to a spatially consistent E field. And its dielectric nature also imposes that it would be polarized. Now, from the previous knowledge of electromagnetism, we can take this equation and derive a dipole moment equation for the dielectric sphere. And we can see this on the slide, where epsilon naught is the permittivity of free space, epsilon is the permittivity of the sphere, and epsilon m is for the medium. The r, again, in this function represents the radius, and k is simply a parameter number that we have defined as such. We know that force is negative of the divergence of the electric potential, and that the electric potential can be written as such where it is dipole moment times the electric field. So if we took this force equation and applied the dipole moment for the dielectrical sphere, we can find an overall gradient force equation that the sphere is subjected to. And from this equation, we understand other such properties of the medium, that other than the properties of the medium and beam itself, we can see that the force is directly proportional to the radius and the intensity of the the beam itself. Now, for the second approach, where the radius is larger than the wavelength, we take a geometric approach where we look at how gradient and scattering forces actually work in the bead. When light hits the bead, some of these rays are reflected and some are refracted into the bead. Hence, the power of the beam can actually be divided into components of reflectivity and refractivity, depending on the angle at which the rays hit the bead and the material the bead itself is made of. So we can actually find a math equation for the scattering force. We know that the momentum of the bead, of the photon is h bar times angular wave vector. And if we orient in such a way that the positive momentum is the photon as it propagates down the z-axis. Now, according to the law of conservation, when the photon is reflected off the bead, since it is now going in the opposite direction, it will have a negative value, and the bead will absorb some of the photon's momentum so that the bead has twice this momentum that the photon originally had. And as force is the change of momentum over time, we can write the force of the bead from the reflection to be written as such, where we see that, and we can see that on the slide. And just to add it, V is, it represents the phase velocity. Now, this scattering force is also called the radiation pressure. And as the momentum has a positive value, the scattering force in the optical trap is always pointed down. So yes, based on this, we understand that the scattering force does indeed have a z-axis component. So if we now what counteracts this scattering force is the gradient force. And we can see this on the diagram. If we consider two rays hitting the bead in the trap, as like in the picture, we can observe that the rays are refracted into the bead, mainly because the photons will lose some of their momentum to the bead itself. And as the laser previously mentioned has a Gaussian distribution, we can also expect that the highest intensities will be located in the middle of the beam waist. Therefore, the force produced from the change in momentum for the higher intensity rays at the center will always have a larger magnitude than the rays that would be, say, located in the periphery. And this difference we can see highlighted in the image. The higher intensity is more bolded than the one that's more in the periphery, just as a visualization. Therefore, regardless of whatever the orientation of the bead is or where the bead might be in the beam waist, we can always expect that the net gradient force will always be pointed towards the center of the beam waist, keeping it, of course, an optical trap. And also the fact that the gradient force has a horizontal component. This is actually why it's called gradient force, because it is heavily dependent on the intensity gradient of the beam. And it also explains why, in order for optical tweezers to work, we would need a laser that does have a Gaussian mode, or this, because it wouldn't work if we didn't have this kind of system. Okay, and to sum it up, just to say, reiterate, scatter force is located downward the z-axis. Gradient force is located in the y-axis towards the center beam. And the only way for a particle to remain in optical trap is if the gradient force is greater than the scatter force. And we define the forces as such, shown in the slide, where we say that Q factors are the dimensionless factors that are dependent on the angle of incidence and of the ray as it hits the bead. And this is just another slide depicting what has been said before. We can observe as the beam is focused onto a laser, the particle is provided momentum from the photons that are refracted and reflected off it. In optical trapping, if the gradient force is higher, we can expect the direction of the momentum that is given by the refraction to always be the dominant momentum, that too being, of course, pointing towards the center of the beam. And now we get to fluid dynamics. As we will be relating speed to the minimum intensity needed to hold the bead in the actual lab, we need to understand the groundworks on fluid dynamics and Brownian motion. In our solution, there are atoms with vibrational energy, and these atoms will eventually hit the edges of the solid particles, or beads in our case, and provide the bead with some momentum that the atoms will eventually lose. Therefore, in the solution, we can expect that the beads will have a movement in them, and we call this Brownian motion. So when we have a bead moving through a liquid, it will experience a drag or frictional force, a sort of resistance caused by the medium. And so in 1851, actually, Stokes, he developed an equation for a sphere moving through a liquid that exhibits laminar flow, so that when and we can see this equation, it is the first equation on the slide, where NF is the effective viscosity, R is the radius of the sphere that is moving, and V denotes the speed of the bead as well. Now, from this, we can understand as a laser that has a trapped bead as it's moving, this trapped bead would obviously, from our understanding, experience this drag force. So we can consider the drag force to be simply another component of the scattering force, which is pulling the bead away from being trapped. And if the laser is moving too fast at a certain speed, it will no longer be able to hold the bead, as the frictional force will overcome the gradient force. Therefore, we can apply a max velocity limit, which is directly correlated to the maximum holding force, where both gradient and frictional forces are equal. And this is shown as the second equation, where we define this as the FH to be the maximum holding force of the tweezers.
Hi, my name is Alex Bergeron, and I will be going over the testing and results section of this experiment. Starting off, the questions that we asked and our expected results. First question was to get down to what's the effective viscosity of the fluid sample. We'll be using Brownian motion for that. Second, we'll be comparing the relationship between the speed of the particle through the medium and the minimum laser intensity required to trap it. Third, we'll be going over the holding force of the beam at each tested velocity and how it relates to the intensity. And finally, we're going to see some conclusions that we at least think theoretically should hold true. So we expect to see a linear correlation between the increase in speed and the increase in the minimum power. We also expect that the minimum holding force will increase linearly with the particle velocity. And then we expect to also see that frictional forces will increase linearly as the velocity increases. Going through the apparatus, as we've spoke about before, the first section of it after the laser is the beam collimator. First it expands the beam and then collimates it, so it will be able to go through the beam splitter, which is the second part, at its full width. Then it hits the focusing objective, in which it's focused onto the slide, and then it will reflect off of the materials on the slide back up towards the camera. The last portion of it is the slide holder, which is the very top of that pedestal that you see in the very bottom picture. And the two motorized sections of the slide holder can translate it in the X and Y direction. The Z direction is translated by a screw. Kind of more of a setup note. The apparatus took many tries to get it to actually trap any particles. We have to go through collimation of the beam multiple times, cleaning of multiple lenses and pieces of the apparatus itself. It was quite difficult, and it took a long time to actually get done. Going on to start answering the questions in which we were asking in the very beginning, the first one being effective viscosity. This is the testing procedure that we followed. So it's a physical property of the liquid that you're working in. You can only find it out through empirical testing. So particles are suspended in medium, and they move due to Brownian motion. You should be able to see that in the video to the very right. As you see, the particles are gently vibrating. That's Brownian motion. By watching that, you can actually understand the displacement of each particle. And once you can calculate the displacement, which is the first equation, the very top under the video, then you can start to calculate the mean square displacement, and then you can calculate the slope of the data that the mean square displacement gives you. So mean square displacement gives you a data point for each time interval, which then you can graph, get the slope from that, and that gives you your gradient m, which then you can plug into the last equation, which is your effective viscosity. Going on to the next question that we were asking, which was what is the relationship between the velocity of the particle in the medium and the intensity required to trap the particle. So first we would start by trapping a particle, as you can see in the video in the bottom right, and then we would have the stage start moving from one x coordinate that was defined to the other one, as you see it doing now. This would repeat for about 20 cycles, and we would continue to lower the intensity of the laser until it would discontinue trapping the particle. Then we would know that that was the minimum trapping, or slightly above that was the minimum trapping value or intensity required. And then we would take that measurement, and finally we would go on to increase the speed of the stage movement, and then we would begin again the process of slowly dialing back the intensity of the laser to see when it would stop trapping. And that was how we got all of our data for the trapping versus velocity. Results of finding the effective viscosity. So first we, as we said, found the Brownian motion. Then we recorded this motion and put it into a software called Tracker that then would take each particle and track it as it moved through the video, which allowed us to get our data for actual positional values of each particle. Then we could calculate the displacement and then mean square displacement of each particle, take the average of all those, and then graph that, which you see in the graph at the very bottom middle. This allowed us to get that m value that we were speaking about before, to understand that slope, which then we can calculate the effective viscosity of the fluid. Now going over the data that we obtained for the velocity and holding force, as you see in the very top right graph, we have intensity on the y-axis and the speed of the sample on the x-axis. We see that as you increase the speed of the sample, you get a linear increase of the intensity required, the minimum intensity required to trap the particle at each speed. Then we went on to calculate the resistive force, which again we used the effective viscosity of the particle, of the fluid, and the particles within it, to then equate that to the minimum holding force, and then plot those, the holding force against the intensity. And again, as you see, a linear relationship between, as the intensity increases, the holding force also increases linearly. And then as you see in the very last graph on the slide, we calculated theoretical holding force required for speeds of a particle, and as you see, that is a linear correlation, so we're showing that we have what we're expecting to be seeing, which is the theoretical says there should be a linear correlation, and as we see, it's backed up by the data that we acquired. As a concluding discussion about the results, we see that our data has definitely held up our claim that there is a linearity between the holding force, velocity, and intensity. However, just to discuss some slight inconsistencies in the data, there's multiple issues The first being that the apparatus was not using a single mode laser, which is the hypothetical ideal for optical tweezers. Also, the laser that was used had multiple aberrations in the lens, and as you viewed this laser from quite a distance away, when we had shown it on a wall quite a ways away from us, we saw multiple diffraction patterns caused by either grit on the inside of the diode or maybe some other issues. Additionally, in our Brownian motion in the video, you can see that there's a slight impulse in the system around 1 second into the video. The screen seems to shake. It must have been from a disturbance of the apparatus while we were recording the data. So that might have, or that contributed to inconsistencies in our findings. However, on the whole, our data, we feel, solidly backs up our claims that there's a linearity between all these values.